Thank you very much. So it's me again, standing in between you and lunch, essentially. We'll try to make it entertaining. For those of you that weren't around yesterday, the whole idea is to have some quick opinions by experts on an important and timely topic. Please, as an audience, also get engaged, ask questions, shout out, just feel free to raise your hand and say something. So in comparison to yesterday, we show you what the session is about now. Just don't say that it's about software stacks. The whole goal is, yesterday was a lot about software stacks, and a software stack is nice, it's a nice skeleton, but in the very end you need to fill it with life and with tools that run that software stack. And those tools all need to talk to one another at some point. And we've heard all the buzzwords at some point. We've heard OpenQASM, we've heard QAR, and MLIR, and LLVM, but as the audience is just 40% computer scientists, many of you might not actually know what this is all about. So I'd like to ask Blake, Bettina and Erick up to the stage to kind of discuss some aspects of that. Maybe something about standardization and also the role of Python in all of this. So you've seen all the three of them yesterday, and I'd like to kind of kickstart it. Maybe each one of you could give a very brief description of what one of those three terms, OpenQASM, QAR, and MLIR mean. And I think you're the one, Blake, for OpenQASM, I guess.
I guess I have to be OpenQASM. So OpenQASM was an effort that started from IBM to try to kind of take what was a plurality of QASMs that it kind of had grown out of literature. I think the original QASM might have actually generated from the Nielsen Schwang book, while they were just trying to find a simpler way to write all the circuit diagrams. But there was sort of a plurality of QASMs, and we tried to kind of bring it all together into something that kind of unified those in sort of a first standard. But OpenQASM, of course, has grown since then, and we've made a more concerted effort to reach out to a broader community to make sure it represents not just IBM interests, but the interests of other modalities, people looking for theory and practice. So OpenQASM today, of course, we have the version 3.0, and it's driven by a technical steering committee that includes parties from across the industry.
All right, QAR, I guess.
All right, that's on me then. I can't explain that without some of the other terms.
Go for it.
All right. So yeah, there's LLVM. It's a framework and chain for building compilers. A lot of the classical compilers are built on top of it. Almost any classical language, no matter whether it runs on CPU, GPUs, FPGAs, has usually some sort of LLVM-based compiler. QIR is a subset of LLVM because LLVM is awesome, but also huge. There's decades of compiler research in there. So for us to actually make use of them, we needed to agree on which parts in that we actually want to use with quantum computing, and that's how QIR was born. It's a joint effort among companies to have something where we can hopefully connect everything together. It's at a particular level in the stack and on the slide at some point, and there's layers above and below, and I'll hand over the mic.
Hello. So I have to explain what MLIR is. And unlike OpenQASM and QIR, MLIR is more general. MLIR is a tool and framework to allow people to develop their own programming languages, and essentially it allows you to also reuse intermediate representations from third parties and compose them neatly, and then you can use their transformations to optimize or define what your language wants to do. And so it's useful if you're implementing a quantum programming language to use MLIR.
All right, I hope that gives a very brief overview of the landscape in all of this. But I think one of the questions that I have for all of you is, who in the room really has to care about all of these intermediate representations? Is it everyone working on quantum computing software? Is it just the compiler people? Who actually has to deal with all of this?
So I mean, I think part of the reason all these exist is that they serve to make connective tissue between different tools, right? We don't have to agree upon what language we're going to build our tool in, whether it's Python or Rust or C++, but we need ways to exchange data so that the developer, the user can build up a stack of the components that fit their need, right? And so it's all about sort of data exchange. And I think we've seen, a lot of the tool developers you've heard from the last couple of days are people that support these two formats, QIR and OpenQASM, as ways to exchange data. And so that's part of what I think, for me, enables an ecosystem of tools to emerge around a plurality of tools.
Anything to add to that? By the way, workload is on now, so you know the drill. Go to menti.com and thanks Daniel was on there. Yeah, it's still on there, so great stuff. I like this idea of unifying the ecosystem and kind of this soft standard of people agreeing on something that we need to support and not doing 12 different things and doing them over and over again. At the same time, like everyone up on the stage, every company behind that has their own MLIR dialect for Quantum at the moment. I know the QE compiler has their OpenQASM version, NVIDIA has Quake, Xanadu has their Catalyst Quantum dialect. Isn't it still one framework but still 5 different dialects all across the world?
Yeah, so here is exactly where it comes in, what tool is good for what. And I think a goal of MLIR is explicitly to make it easy to customize. Because while there is a general set of tools that all languages need, like, walk the AST, replace nodes, get all the dependencies and so on. Part of the reason to have your own front end is because you want to introduce certain abstractions that are particularly useful for optimization, right? Otherwise, we wouldn't need our own language, basically. So MLIR allows you to keep that with the idea that you progressively use these abstractions for optimization and eliminate them, right? So you're lowering, right, at this point. And this is exactly why, on one hand, originally, when we decided to go with kind of LLVM as an exchange format, MLIR was less long on one hand, but also, it doesn't feel like necessarily the level to standardize on. It's the level to customize on. At the same time, there are, I think, parts at that level with some abstraction. They are also pretty common among different frameworks. There's a lot of frameworks for now that have some sort of MLIR classes and infrastructure that they leverage. And it's a good conversation. Some of these interfaces, I think, can be aligned on, so that it can have passes plugging into different frameworks, but maybe not everything, right? And then as you get lower and lower, below LLVM, there it starts to be very custom again because hardware is very different, I think.
Yeah, I completely agree. I think MLIR works really well for customization. And I believe that there's probably a large amount of subset of operations that are very similar, probably among our dialects, and that could potentially serve as a point to start a conversation about maybe standardizing potential dialects. But we need to talk more about that later.
How do we actually make that happen? Like, I like the idea very much of sitting together at a table and figuring things out, but I mean, we're all in the room now. Should we just lock the doors and talk about it and come out with a standard? Or what's the goal here? How do we do this?
I guess I would put the brakes on a little bit from my perspective until rushing towards standardizing this, because for me at least, like, the use of LLVM for compiling quantum circuits is still kind of an unproven thesis that it's a good idea. Right, like it's obviously got a lot of rich history in terms of quality of classical compilation, but we're kind of teaching it everything about quantum circuits, right? It comes with nothing. So like the fact it's maybe it's a convenient tool, but like we still haven't proven that it's a great one for the purpose. And so I think we need to still enable this kind of creativity, exploration, rather than trying to nail it down before we've actually like really gotten comfortable with the idea itself.
Would you agree with that?
I don't see why we have to pick one or the other. I think, I guess maybe we're talking about standardization, so maybe a little bit. But I find useful to have like a framework that focuses more on experimentation, for example, and another one that just focuses more on like reusing and sharing the tools that other people have already developed, and that we know that somehow like work sufficiently well enough for current use cases. Yeah.
So maybe to get the audience involved a little bit, like LLVM, MLIR means C++. Everyone in the quantum computing community loves Python. So how many of you in here have actively worked with LLVM at some point in their development, software development career? Hands up, please. It is quite some people, but I think like 80% in the room haven't at all. If we now adopt that as a standard or as a standard way of doing things in software, how do we make these people work on such a software system that they're not comfortable with?
I think this comes back a little bit to your question of who should care, right? And I would say a good next progression, I think, for quantum computing is to really start making this distinction between what needs to be at the application level and what's really part of a stack, or maybe at some point even firmware and so on, right? So for the tools that we talk about here, this is squarely within the compiler. This is not intended to be easy to read for a human or write. Yes, my engineers occasionally handwrite LLVM or MLIR, but that's not per se, what you should be doing. So, the question comes back to, maybe we can also have a raise of hand of who's working specifically in the compiler, not how to compile specific applications, but like general compiler framework.
Right, hands up.
Seems an overlap.
Inside.
A different thought to add here. I mean, so I think one of the challenges that we face, particularly with compilers and so on, is that we still are getting a lot of benefit from algorithmic advances rather than engineering advances, right? I think it's certainly true in my organization that most of the theorists that are coming up with new algorithms for circuit compilation are not software engineers, right? Very few of them are really comfortable with C++, like maybe the only programming language they know is Python and maybe something like Mathematica or something, right? So one of the concerns that they had watching us when Gits get converted to Rust was like, well, but how am I going to provide an implementation of my new algorithm? And so I think this is a kind of a scary thing when you're sort of looking at how do you keep a research to development pipeline that is fat so that those ideas can quickly emerge in software that people are using on a day-to-day basis. It kind of reminds me of something that I encountered almost 10 years ago now that was looking at the relative power of algorithmic versus clock speed advances in computing technologies. And I guess maybe this is another show of hands. If you were to take sort of modern algorithms in a variety of disciplines, whether it's like machine learning, natural language processing, search from today, and ran it on a 1982 Intel 8080 processor, do you think those algorithms would be faster? Do you think you get a faster thing using today's algorithms on slow hardware, or the algorithms from 1982 on today's hardware? Can we get the show of hands for algorithms win? Only a couple. What about hardware wins? All of them. So the surprising result from 2011 was that algorithms went hands down. And so this is kind of one of the things that for me becomes a little bit intimidating, that we're sort of putting up barriers to entry for algorithmic advances, which is why I'm often trying to kind of hold open the door still for our researchers to contribute to compiler development.
Sure.
So we wanted a heated discussion, right? That's what you're here for now.
I'm standing right in between you two. There's no fight.
All right, I mean, definitely the whole point is to accelerate basically development on all fronts, and specifically also algorithms, right? My kind of desire here is to really start building trust in automation and the compiler in some sense. I think this has been one of the main hurdles a couple of years back. People like, well, no, don't optimize automatically. I know how my algorithm is supposed to be optimized, and who knows what the compiler is doing. It might do something horrible to it, right? And the thing is, while it's completely reasonable to want to have the comparison against what if I hand optimize like basically everything, right? And tell it exactly what the machine needs to do. How well does that look? It's a good thing to be able to do, but not sufficient. Because the reason being, my generation, I feel old now, was still the time when a PhD in that area included spending 4 years to optimize a single application. That's great, but I took a different path. I was like, great, I've got 4 years now. Let me start writing a compiler and then run it at the end and see what it spits out, basically, to do that. And when you do that, you don't get one application, you get hundreds pretty quickly. And it may not be 100% as good as the hand-optimized version, but it will get you there. 90%, 95%, and so on. So that allows you to filter a ton of things that aren't very useful, very good at the application level. And then you can focus on the things that actually matter. This is why we need automation.
I wanted to comment on Blake's comment about the need for having the openness for supporting Python, for example, and more of a scientific research, not so much as a software development. And yes, I agree completely with that. Again, I think there's place for standardization somewhat, but we don't have to pick just one to rule them all. And I also want to highlight that there are some ways to get started with MLIR in Python. So for example, XDSL is pretty cool, and it's a good way to start teaching compiler concepts to people. And it's compatible with MLIR, which I think is pretty cool. Thanks.
So there's a question over there and then over there. Just shout it out.
Yeah, so to go on, so Billy, you were talking about like trust in compilers, essentially. So with regards to these intermediate representations, are you taking into account like use of form verification techniques? There are things that exist out there like VLVM, which is like a verified LLVM framework. So I'm not sure any of you have considered that in your designs.
Love to. Do you want to start working on it? In all seriousness, every now and then there's always this one person that asks me, yeah, great, let's get this going, and then it takes 2 months to get to a conference to find the other person. I don't have the expertise, frankly, unfortunately. I know it exists. I know a little bit about some tools and talk, but that's it. It's never gotten to the point where it was ready to pull it into production, basically. Yeah. But I think it will be really good, especially gate set mappings and then transformations on these things. You know, that could be formalized really well. I mean, to an extent, verified compiler passes and all of that. And given how hard it will be to debug quantum hardware when you can't run it on a simulator, I think we should really start pushing on making the software as reliable as can be.
Maybe I can even add something to that, because it's a question that is very dear to my heart. Verification and equivalence checking. Alex, you talked about it with SynX diagrams, with SynX calculus, doing equivalence checking with that. We've been doing this for quite a while, also with other dedicated data structures that you could be using for that, and to trying to get the message across that please, people, you're right optimizations, you're still just humans, you make mistakes, verify what you're doing, please. And it's not, at least for the scales we're currently looking at, it is not impossible. We can still do this. There are tools and clever data structures that allow you to verify now that what you're doing is actually what you expect to be doing. So there are tools out there, and you should be using them. And yes, some of the people might lack the expertise, so it's also on us to develop tools that are easy to use and to just plug and play into there. It's just another checkbox that lets you pick, hey, I want to verify my result, and that should work without taking weeks. But we're getting there, and people need to adopt this and start to use these tools as they're available. Verification is always an afterthought for many people, and we've seen where this leads to in classical certain systems, where we can never hope to verify any of the chip designs completely. Raphael?
I think there was
oh, yeah, sorry for that.
I just wanted to mention, we have 3 representatives from hardware companies. And and when it comes to software, hardware software, it's me from software, it's it's just a different mindset. It's mostly like, when you're a hardware company, your business depends on the hardware. And the way that you handle software is always for the benefit of the hardware that you're producing. If you think it from a pure software company side, his story has many different faces. It's just that it was just we can discuss later. Whoever is interested, I have a lot to share. I just wanted to say it's much more than those three options that you added there. I know hardware are big players because they're producing hardware, but don't underestimate this. So it's just
Yeah, thanks for the comment. I think that list is non-exhaustive for sure. I mean, there are things like CRISP, there are things like Hugger that are around for intermediate representation. So many people are actually thinking about how can we represent programs in what way, which abstractions do we need? Like what Michael was hinting at earlier, this abstraction hierarchy and the working group on that. So there's many people working on this, and sometimes these people should meet up and maybe try to agree on something. Raphael, you wanted to say something?
Yes, I actually wanted to go in a different direction. So my perception is that recently hardware vendors became a bit hesitant to actually offer this real-time features because they fear that evil people on the internet are doing something bad to their expensive equipment. How do you expect this to turn out? What's the game plan here to make this still happen?
Gonna hand that to the hardware provider first.
I guess I'm curious as to where you're seeing that, because at least for us, right, we started operating dynamic circuit capability
Actually, I asked
2 years ago.
I asked Beta in May in San Sebastian, and he said that he was not so sure about this.
I mean, there's various ways in which the real-time capability that's available on our systems will evolve over time. And particularly at this point, we've executed about 1 million jobs that are sort of dynamic circuits, which is a large number of jobs, but it's actually just a drop in the bucket of the total job volume when it comes to IBM systems. And so we've been kind of digging into why they're sort of not more popular. And one of the reasons that we believe, right, is that we're in some ways failing to deliver the value statement of dynamic circuits, which is be able to trade off kind of width and depth by kind of choosing the circuit measurement and doing short computations on those in order to sort of grow entanglement faster, for instance, or repair states in shorter depth. But sort of when you go to deploy that in practice, people will end up wanting to do those in parallel on multiple parts of a circuit simultaneously. And our current execution model forces it to be serial, which kind of very quickly start to lose the benefit of the dynamic portion of the circuit. So we're been kind of rebuilding our runtime infrastructure to address this problem. So the future of dynamic circuits for us will be more highly parallel, and it's kind of an attractive thing for us to invest time in now too, because that's also exactly the structure that you have in an Erick component system, where we're doing the checks and P ports for Clifford gates has exactly the structure of the dynamic circuits that are sort of locally parallel across the system.
Maybe more so from the software compiler side, how do we actually deal with these dynamic capabilities, with these real-time capabilities? How tightly can we couple the quantum computer and the classical computer, like from both of your sides, from both of your software stacks at the moment, and in the future?
I'll try to chime in here and then add something on security, because I'm just coming from a half-a-year conversation about security. So how tightly can we couple things? Well, in principle, very, very tightly. That's the whole idea, and we definitely need that for at least error correction. I argue that since we need it fundamentally, you might as well use it for applications as well. And I think there are benefits. There's a lot less research on adaptive algorithms, since this has been, more recently feasible, and there are hardware providers that do offer that. So I do think it's very well worth its my opinion, the notion that all quantum computing is going to be good for is one gigantic unitary leads just to the argument of, well, it's an input-output problem. It's never going to be beneficial because you have too much input and output you need to get out. Well, not if you have slightly different algorithms. You know, maybe more online processing things. Don't read in a gigantic database at the start, then do the quantum compute, then get everything out. You know, keep reading piece by piece, process live. That'll lead to much better outcomes, I think. And this is why I want this feature and want you feel encouraged to look into that. It's possible. Now, security is a challenge. So, yeah, regarding high coupling, NVIDIA is very good at building high coupling, high bandwidth, fast connections. You know, this is what we do with Grace Hopper chips. We work with some hardware providers to see how fast exactly we can get that, and I'll keep you posted. Security is a real issue. Now, mid-circuit branching, not a problem. Adding two doubles, not a problem. All of this is not security relevant and not an issue. Pointers, very much a problem. You know, so there are things that, yes, everybody that offers something by the cloud and gives people the right to do pretty much arbitrary things, you'll need to check at some point very carefully at what you can do with it. And it's not distrust towards you per se as the user. You know, it's very nice. The quantum computing community today is great, but at some point, when this becomes actually useful, suddenly everybody might be there and doing things, and even accidentally, you know, overheating the system or whatever you can do with it. You know, so it does come down to every cloud service provider has their dedicated hardware and security infrastructure to exactly protect also your IP and everything you run on it. And that just needs to be also kind of built. And here is where, you know, we've been very, very focused on hardware for a long time. So some of these standard software aspects just lag behind a little bit because they weren't under as much pressure to be built and develop and to use. I think they're going to be there.
In terms of security, compilers also help because they can do program verification at compile time. And I want to highlight one specific technology. So eBPF puts essentially a virtual machine in the kernel that's user programmable. But before, so just as you can imagine that allowing the user to run programs on the kernel is very dangerous. But before it runs, like this virtual machine is very strict, and it will make sure that it will terminate by, for example, making sure that there's loops, the loops are bounded, there's no recursion, etc., etc. So you could imagine some security features be also implemented via program analysis to make sure that some of the hardware isn't damaged by the user, even by error or by some ill intent.
So before we head for lunch, there's one comment question over there. Matthias, go ahead.
Question. Given that there are so many hardware platforms, each of which needs their own compiler, and it's considerable development overhead to use something like MLIR or even Rust, but not to the extent. My question is, what is the concrete pain point you solve at the moment using these tools, besides speeding up the compilation?
Probably gonna hand that to the left side over here. So one of two of you.
Using API, using all sort of classical libraries, uploading some part of applications or compilations to other accelerators.
This is an abstract thing, so concretely for a circuit I submit at the moment in compilation, which I cannot do with the Python compiler, for example.
You can do anything in infinite time, right? So you need to be more precise of what the problem statement here is.
Yeah, I mean, for sure it speeds up compilation time, but using external libraries, what concretely solves that for me in the compilation process, using this external library at the moment?
I think the external libraries help you to a good degree for applications on one hand, and the kind of applications you look at might be slightly different. If you need to rebuild MPI to look at some parallelization, you're probably not going to do it. If you have it readily available and usable, or more tempting to actually use it, right? And similarly, you know, there's a whole lot of Linux libraries, you know, NAPAC and so on. You really want to go rebuild them.
Erick, you want to? That's it. All right, then last thing before we head for lunch. It was a great discussion, but I haven't got an answer to the one big question of how do we actually proceed with agreeing on something? Like, should we lock the door with a set number of people? Should we just keep you here for another week? Like, what do we do about this? Maybe talk about it over lunch?
Yeah, talking about it over lunch, or also, I guess, if we all have like a forum where we can chat, even informally, that could also be like a good starting point.
I think some follow-up meetings from my end are eagerly sprouting up, which I think is good. General notion is agree on the problem first. You know, we can't talk solutions if we have a different understanding of what we're solving.
I guess I would add that these communities exist and are often looking for people that are committed to actually doing work to make a difference and change something, right? The kind of gating nature of changes in OpenQASM isn't like interest. It's actually just like people do the work, not just propose the idea, but then actually go try it out in practice. So if you're one of those people, we would love for you to join our bi-weekly conversations about OpenQASM.
All right, let's do it. Let's get to work. Let's get to lunch. And enjoy lunch. Thanks everyone for staying around.